We have our next speaker, Reynold Fregoli from University of Zurich. He's going to talk about multiplicatively badly approximable vectors.
Thank you very much. Okay, so today I want to discuss some kind of weakening of the Littlewood conjecture. So probably I should start by recalling what the conjecture says. So I think it was formulated around 1930. And it says that for every pair of real numbers, alpha, beta, see in R2, one has that the limit for q tending to infinity of q times double bar q alpha times double bar q beta is equal to 0. Now here q is just some integer, and by double bar x, I just mean the distance from x to z. X is just any real number. Okay, I will call it fractional parts sometimes. It's a slight abuse of notation, but I guess it's still fine. Great, so this statement sounds a bit, strange maybe to some of you. I just want to say a couple words about the motivation behind this conjecture. So the thing is, if you have a pair of real numbers alpha beta and you are trying to approximate it with a pair of rational numbers p1 over q, p2 over q, well, you might want to study the quantities alpha minus p1 over q and beta minus p2 over q. So how well you approach the vector alpha beta, and in what we call multiplicative setting, we like to study the product of these two quantities. Okay, so what can you say about the product of these two quantities once alpha and beta are fixed? Well, if you also fix your denominator small q, then you can always find p1 and p2 such that the product of these two things is smaller than 1 over q squared. This is obvious for any small q. However, there is some kind of pigeonhole argument, which is essentially the same as Dirichlet's theorem, which I want to call multiplicative Dirichlet. That says that, so for every alpha beta, there exist infinitely many q such that alpha minus p1 over q times beta minus p2 over q is less than 1 over q cubed for some p1 and p2. Okay, so you cannot do you cannot do better than 1 over q squared for any q, but at least for no, for infinitely many q, you can approximate this product is small, smaller than 1 over q to the power 3. Okay, so you can do better than 1 over q squared, which is kind of the expected approximation. And the point is, can you always do better than 1 over q cubed? So if you cannot, if there is some pair of numbers alpha beta such that you cannot do better than this, then there exists some epsilon positive such that alpha minus p1 over q times beta minus p2 over q is bigger than epsilon to the power 3 divided by q to the power 3. So essentially, the conjecture says that independently on alpha and beta, you can always do better than 1 over q cubed, but you don't know how better you can do. And the point is, we don't know if this conjecture is true. But there are some nice results. So we know, maybe let me just call it LC. We know that LC is true for almost every alpha beta. And also there's an even stronger result by Einsiedler, Katok, and Lindenstrauss in, I think it was 2006, that says that the set of counterexamples, so counterexamples to the little conjecture have dimension 0, Hausdorff dimension 0, or even, okay, probably box dimension, but anyway, Hausdorff dimension. Great. Okay, so this is what we know about the conjecture. And okay, if you look at this expression, you see, okay, or at this, say, approximation process, you see two numbers. But what stops you from considering more than two numbers, right? So analogously, you can consider something like this. So you can ask if there exist vectors alpha in Rd, where alpha is something like alpha 1 dot 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 alpha d, such that, let's put a question mark here, such that the limit for q tending to infinity of q times fractional part of q alpha 1 dot 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 fractional part of q alpha d is positive. Okay, so this is something like a higher dimensional Littlewood conjecture. And the point is, even this statement is not known to hold for any vector alpha. But one thing that I would like to draw your attention to is that if this statement here is true, so if the two-dimensional statement is true, then definitely the higher dimensional statement is true, because you're just multiplying by a bunch of things that are smaller than 1. Okay, great. So we can't say much about this. Well, if you look at this expression, you will see that you have on the one hand something like q, which grows, and on the other hand you have a product of fractional parts which are sort of, they're all smaller than 1, and somehow this should push this slim inf to 0 somehow. So perhaps if we change this factor q that multiplies the fractional parts, we have a chance of saying something, of finding a vector alpha 1, alpha d such that this slim inf is positive. So a natural question is the following. So question. So can I find f from R to R increasing such that this slim inf q tending to infinity of f of q fractional part of q alpha 1 dot dot fractional part of q alpha d is positive for some, for at least one alpha in Rd. Okay, so maybe if I change q, I have a better chance to do this, right? And so, okay, so there's a nice result in this direction, which is Gallagher's theorem. Many of you know about this result. So suppose that let me introduce this set here, MDF, which will be the set of alphas in Rd such that this slim inf is positive. So the alphas that do what we want. Dot q alpha d positive. So limit of this expression with f positive, then Gallagher's theorem. I think this was around 62. Okay, so it's not a very new result. It says that the measure of this D is the dimension. Okay, so and the Lebesgue measure of this set MDF is, let's say it's 1 if, okay, MDF is a big set, so probably it's worth intersecting it with the unit cube. Okay, so now the measure is either 1 or 0. Okay, so then the measure of this set here is 1 if this series here, so f of q to the -1 log q to the power d minus 1 converges, and it's 0 if this series diverges. Okay, so this is one of the usual 0-1 results that we all that are so common in Diophantine approximation. And well, actually, what Gallagher did is he looked at the opposite inequality. But if you twist a bit what Gallagher proved, you essentially find something like this. Okay, and right, so now if we go back to the setting of the Littlewood conjecture and you take f of q equals q, so this is the Littlewood conjecture, well, you will see that this sum here, q to the -1 log q to the power d minus 1, is divergent. So essentially, Gallagher tells us that the set of vectors that we are trying to find has measure 0, right? And well, a natural family of functions to consider if you want to say something about this convergence or divergence is the following. So for lambda positive, you can consider functions of the form f lambda of q equals q times log q to the power lambda. Okay, so the Littlewood conjecture is f0. Okay, but if you plug this f lambda of q into the statement of Gallagher's theorem, you will see that what you have is that md f lambda intersect 0, 1 to the power d has measure 1 if lambda is larger than d, and measure 0 if lambda is between 0 and d included, right? I just plug a q times log q to the power lambda here, and well, we know that 1 over q times log q to the 1 plus epsilon is a convergent series, right? So essentially, as soon as lambda is bigger than d, in this series here, you have 1 over q log q to the 1 plus something, and you're happy. Okay, so right, so now if you look at this statement here, well, you will see that there's quite a lot of room for improvement, right? So essentially, the Littlewood conjecture says that M2 of f0 is empty, right? But we also know that we also can't say anything for, or at least for now, we haven't been saying anything about functions for which lambda is between 0 and d. Gallagher's theorem only tells us that if f is too big, if this exponent is larger than d, then definitely, okay, what we want to do is trivial. So there are too many vectors that are in that satisfy that inequality. So lim being positive. Okay, so so now the interesting range for lambda is lambda between 0 and b. Okay, and well, there have been some results in this direction. So actually, one of them was recalled by Jan Bujold yesterday, and so see the first one was proved by MOSCHE and Bujold in 2011, maybe. Correct me if I'm wrong. And so they proved that for d equals 2, so in dimension 2, one has that the set M2 f of 2 has full dimension. So in particular, if you unwrap the notation that I'm using, this means that the set of alpha beta such that limit q tending to infinity of q log q squared, fractional part q alpha times fractional part q beta is positive, has full dimension. Okay, so we are in the case lambda equals 2. So at the very at the very edge of the range of interesting values of lambda. And so we know that our set, the set of alphas that we are interested in, has measure 0, but it has also full dimension by this result. Okay, and can I use this board, or is it too far? Maybe, yeah, okay. Ah, okay, great. Okay, tell me if there is something unclear, or maybe if I'm writing too small, too big. Fun? Where? Yes. No. In Gallagher's theorem. No, because it's the opposite inequality. You're looking at this, so you want badly approximable, not well approximable. Okay. Yeah, sorry, maybe I'm. It's not the best way of presenting it because people are used to one form of Gallagher's theorem, and I'm presenting the opposite. But it's the same thing in reality. Okay. Great. So let's see. A proof of Gallagher's theorem. Yes, I think there's a way of, somehow I think you have. So I did it for fun because it's useless. So Gallagher proved it in a number theoretical way, but essentially, if you use the action of a multi-parameter group, and then you use some form of equidistribution, you can reprove this result. For any increasing f. For any increasing f. If f is not increasing, there's very little you can say, even with number theoretical method. Okay. Great. So the next step in this sort of in the history of this result is BADZIAHIN's result. So this is, I think, 2013. So just a couple of years later. So after Jan Bujold and MOSCHE proved their result. So he showed that again in the case d equals 2, one has that M2 f of lambda has full dimension whenever lambda is larger than 1. And actually, so he essentially improved on that result there. So there you have that the set has full dimension for lambda equals 2, and now you have like a whole new range of values of lambda. So actually, he proved a slightly stronger statement. What he proved is that the set of alpha beta such that lim q tending to infinity, q times log q, this would be f1, but f1 is not good. It doesn't lie in this range. But if you add a log q, so a double log, then you have full dimension again. Okay, the set of alpha beta such that this holds has full Hausdorff dimension. Right, and okay, so let's see. Yes, I forgot to mention that in between these two statements, okay, I'm not going to write it, but there was an intermediate result by BADZIAHIN and VEIANI, who proved the same the same kind of statement in the p-adic setting. So where instead of two fractional parts, you have one fractional part, and then you take the p norm of q. So the same statement hold. And unfortunately, for now, nobody has been able to say anything for lambda between 0 and 1, or for lambda even equal to 1. So we don't know what can be said in this setting, even in the p-adic case. But what Jan Bujold presented yesterday is essentially this result here in some kind of dual form in the p-adic setting. Okay. And yeah, so just to finish this kind of introductory part with an open question. So there is a conjecture. So conjecture by BADZIAHIN and VEIANI. And they conjecture that the set M2F of lambda should be empty for lambda between 0 and 1, and full dimension, a full dimension set for lambda bigger or equal than 1, greater or equal to 1. So essentially what they say is that BADZIAHIN's result should be improved to include the case lambda equals 1, and as soon as you go below 1, you should find an empty set. And so this conjecture is actually stronger than the Littlewood conjecture, because you're saying that the set not only should be empty when lambda is equal to 0, but also for larger values of lambda, which is a more complicated thing to prove. So for now, this seems completely out of reach. Okay, but so in their favor, the sentence is by a volume argument of Peck, but I'm not sure exactly what this volume argument is. So somehow, so if you look at these multiplicative sets, right? So their volume is something like log q, right? More or less, this log q should be a factor that discriminates between empty and non-empty. But I can't be more precise than that because I have no idea. Okay. But yeah, so for now, we don't know. Good. So what is my modest contribution to this picture? Okay, so yeah, so So this is a result that I proved together with Dmitry Kleinbock this year. So whenever D is bigger or equal, so larger or equal than larger or equal to 2. So essentially in any dimension, one has that MD F of lambda has full dimension for lambda larger, strictly larger than D minus 1. And so this is essentially a generalization of this result to arbitrary dimension. And actually, again, what we proved is a stronger statement. So stronger statement. We proved that the set of alpha beta such that, sorry, not alpha beta, but alpha 1 dot 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 alpha d such that lim q tending to infinity of q log q to the power d minus 1. So this is the case lambda equals d minus 1. And with an additional factor log q times the product of these fractional parts is positive, has full dimension. So has full dimension. Okay, so essentially in higher dimension, what happens is that you only have to increase the power of log, and you can leave the log as it is. And this is probably a hint to why this conjecture here should be true. Somehow, when you increase the dimension, you have something that is not sensitive to this increase in the dimension anymore. So I take this as a hint as to, a hint of the fact that probably this factor here is unnecessary, but the techniques that we're using for now do not allow us to remove it, okay? Great. Good. Okay, so let's see. How I have how long? 20 minutes? Half an hour. Okay. Okay. Great. So probably I won't be using the whole. Dimension 2. Yeah, so it's just the dimension minus 1. So the power that you should put here is the dimension minus 1. Oh, that's what you mean. Yeah. I think, let's see. Yes, that's true. Okay, yeah, I was too modest. I actually didn't prove this. So what we proved is that you can find vectors. So you can find vectors such that each component has the right, each subvector is in the right set mad lambda. So it has the right exponent. So what you say is true actually. So you can actually find the right dimension in each subvector. And also, for who is familiar with this, the whole vector in each subvector satisfies a dual version of this statement. Okay. So, right, let me write it. Maybe it's. So what we proved is that, so the set of alpha in RD such that for every I between, say, 0 and D, oh, sorry. Let me put it like this. So for every I contained in 1 dot 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 D, I non-empty, okay? The vector alpha I, which is the vector of the components in the set I, lies in, I didn't define, yeah, I called it this, so mad cardinality of I, F cardinality of I minus 1, okay, has full dimension. And actually here you can also put a dual version of this, which I don't want to define because I don't have, probably I don't have the time, it would confuse. So let's call it star, okay? So each subvector satisfies something like this with the right exponent. So I'm saying not only satisfies something like this, but also a dual version of this. And the dual version is where you have, okay, a linear form, right? Okay, great. And actually this seems necessary for the proof. Somehow I couldn't prove the statement without proving something strong. So, okay. Right, so in the remaining time, I want to give you like a vague idea of how the proof is structured, only very vague because there are lots of so there are not that many ideas, but there are lots of technicalities. So I will try and explain the ideas. Okay, so the main ingredients. So the main ingredients are, so one, a multiplicative Dani correspondence. So which is a generalization of the usual Dani correspondence. So thank you. And number two is a so sharp non-escape of mass. So I'm going to explain what I mean by this in a moment. Okay, right. So let's maybe take a look at the multiplicative version of the Dani correspondence. Okay, some of you will definitely be familiar with this, but let me just say a few words. Okay, so this correspondence is essentially a dictionary between Diophantine approximations, so between something like statements like this one, and dynamics on the moduli space of lattices. So let's restrict ourselves to dimension d equals 2, and say to each pair alpha beta, we want to associate a lattice of this shape. So a lattice similar to what Uri was considering yesterday, a unipotent lattice like this. And we want to see this as an element of SL3R mod SL3Z. And also on that space, we will be considering the action of the full diagonal group. So something like e to the minus t, e to the t1, e to the t2, where t is just the sum of t1 and t2, and t underlined is the vector t1, t2. Okay. And now let me, so with this notation, let me state this correspondence. So we have that, so q times the fractional part of q alpha times the fractional part of q beta is larger than, say, some function h of q. So for simplicity here, I want to separate the function f that I'm considering into two components, one q that I want to leave on this side, and one h of q, which I want to put on the other side. But this is nothing too strange. So essentially, I leave the q here, I put the log q on the other side, okay? So h will be some, so non-increasing function, okay? And you have that this is true for every q in n, if and only if. So here I have Diophantine approximation, here I have to put something dynamical. So if and only if the action of AT, so AT acting on this lattice, which I will call, so this lattice here, I want to call lambda alpha beta. Okay, so AT acting on lambda alpha beta does not intersect some neighborhood of infinity, which I will define in a moment. Okay, for all t in some set C, let me call CR. So there's a lot of notation here. I will explain in a second. And so what is UT? So UT is essentially the set of lattices lambda in SL3R mod SL3Z such that, okay, let me erase this. Such that the first minimum of lambda is smaller than e to the minus RT. Okay, and R is some function, so R is an increasing function that has a direct correspondence with the function h that I have on this side. Okay, so I have a map that tells me whenever you give me h, I can find r so that this statement is true, and whenever you give me r, I can find h. This is something proved by Kleinbrock and Margulis. So it's one of their lemmas, technical lemmas, essentially. Okay, and what is the set CR? So the set CR is the set of my times. So all the times that I have to use to for which I have to ensure that this statement here is true. And CR is something like T in Z2 such that Ti is larger than minus RT. So I have to allow some negative times if I wanna study something like this. Okay. So essentially, one would usually expect that the set of times that you consider is just the positive quadrant. But in reality, depending on what function you put here, which spits out the function r, you will have to consider a slightly larger set of times. So something like this. Okay, and if you want to see this pictorially, what you will see is just essentially, this is your space of lattices. Here you will have some torus sitting in the space of lattices, which is essentially the set of lattices lambda alpha beta when alpha beta is ranging in R. Okay, it forms a torus here, and then you have your neighborhood of infinity, UT. Okay, and essentially you start from your point here, you act through the flow AT, and you don't want the flow to enter the neighborhood of infinity. Okay, so essentially this is some kind of a non-shrinking target problem. I have a shrinking set of shrinking family of neighborhoods. I don't want to enter them. Okay, so good. So what's the most kind of naive approach to a problem like this? Well, if you look at the picture, maybe let's go back. Okay, so the naive approach to this is the following. So I have my space. My proof is going to be a proof by picture. So I hope nobody objects. Okay, so this, say you start from some square of lattices here, and you have this shrinking family of neighborhoods, and you take your, so you act on your square through AT for some time t, and this square will expand, become something like this. And then you say, okay, so all the points that through the action of AT have entered the cusp have to be eliminated because they don't satisfy what I'm asking. So the good points are the one lying in this part of the square, which I then can see on this side here. So I can contract again and see on the original square, okay? And then I keep repeating this for all times t, right? But there's a problem with this. And the problem is that t is a vector. Okay, so this is essentially what Kleinbach and Margulis did in, well, to prove the analogous case of a one parameter flow, okay? But here you have a vector. So in reality, you don't, so you can have t's times that have components that are more or less the same in size, or one is very small, the other is very big, or the other way around. So you don't just get a nice square here, but what you get is might be something like this or something like this, okay? And when you cut out whatever has entered your neighborhood and you take it back, well, what you see back is just some mess. And it's very difficult to construct some Cantor type set. So, sorry. I was too far. So it's very difficult to remove all these squares and say that what's left is non-empty. Okay, so you for each time t, you have to remove all these things. So I have some points that have entered the cusp, they're bad, I have to remove them. Remove. I want what's left to be non-empty. But because of this, because the shapes that I have when I go back are very bad, I have a problem. Okay, so a better idea is the following. So you have your space, and you, instead of a square, you fix one fiber in your torus. So say fix beta, okay? And consider a segment here. So take something like x beta, such that x is in some interval I, okay? And then, well, you play the same game. So essentially you start from your segment, you apply the flow AT, this segment will expand and you say, okay, these points here are bad, I want to get rid of them. And then I contract back and I will have some, maybe I can use a different color. I have some, oh, this is really bad, maybe yellow. Okay, I have some things which are good and some intervals that I have to remove. And so now what I remove are not sets with very different shapes. They're all intervals. The only thing that I care about is just the size of these intervals. Okay, so this approach works much better. Okay, so this is the Dani correspondence part. And now let's take, how much time do I have? 15, okay, great. Okay, so now let's have a look at this second ingredient. Yeah, perhaps I'll get it. Well, I mean, so this essentially is a way of saying, so I want to say that the points that are left, so that there's at least one point left after all these checks, right? But this means that the only point that's left is bad, badly approximable, right? So this would, if this worked, in the case of, so not for a shrinking set of neighborhoods, but for one fixed neighborhood, right? That will give you the opposite of the Littlewood conjecture. So it would disprove the Littlewood conjecture. Does it make sense? Yeah. Okay. But the idea is we are trying to say that the set of badly approximable vectors is non-empty, right? So if you pick the function h to be a constant, then you will get things that contradict the Littlewood conjecture, and then, okay, probably. I don't think this argument works to disprove the Littlewood conjecture. Okay, great. Right, so now, hopefully I haven't confused you too much. Okay, so what do I mean by non-divergence? So by sharp non-divergence. So essentially, right, so we are doing this thing for every time t. So we're playing this game. I have this fiber, I expand it, I have the corresponding neighborhood of infinity, I cut out something, and I take it back. And I do this for all the times t in my set CR, and I hope that something is left at the end. But then if I want to have a hope that something is left at the end, I must ensure that not too much of this fiber goes into the cusp. So I can't remove too much at each step. Otherwise, the Cantor set that I'm left with is, well, essentially empty, right? So this means that if you have some, so your interval here, I, and you have your ut here. So let's probably give a name to the things that we want to remove. So the intervals that we want to remove are the x and I, such that the first minimum of at lambda alpha beta is smaller than e to the minus rt. Okay, for all t1, t2. And non-escape of mass means the following thing. It means that the proportion of things that goes into the cusp is not too big. So non-escape of mass is the following. So for every interval I prime contained in I, my hope is that the measure of things that I remove at each step t, which I call dt, intersect I prime in proportion is not too big. And what I mean by not too big, and the proportion should be exactly the proportion between the volume of the neighborhood that I want to remove and the volume of the whole space. Okay, so essentially, I want to say that whenever I have some segment here, right, the part that I want to remove, so the part that I see here, has the same proportion in the expanded segment as this part of the this bad neighborhood here has in the whole space, right? And okay, essentially this is what I want to ensure. This is a non-escape of mass, and this has been studied many and many times over by Kleinbock, Margulis, and so on and so on. So I will conclude in a minute by convincing you why this is the right thing to prove, okay? But what I want to say is that unfortunately, so you might say, okay, so why, if you want to prove something like this, why don't you use what Kleinbock and Margulis proved? So their version of the non-escape of mass. And so it turns out that what they prove is that essentially the proportion of points here that go into this bad neighborhood of the cusp is not exactly the volume of this neighborhood, but the volume to some exponent alpha. Okay, so it's just slightly smaller than what you want. So you need something really, really strong. You need a really sharp version of non-escape of mass to obtain something like this. And if you have something like this, then you can conclude, and I will show you why. Okay, so you need to prove something slightly stronger. So let me just conclude by saying why this gives me what I want. Well, the reason is kind of simple. So you have your, say, your initial interval I, okay? And here you have, say, suppose that instead of removing dt sparsely, I remove, so I fix, say, a big T, okay? And I call D sub big T the union of T1 plus T2 equals big T, D T1, T2, okay? Then, well, how many of these sets do I have? So the number of dangerous intervals, so this is the name that we give to these intervals here, that form this set dt. So dt contains big T dangerous intervals. Sorry, yes, big T dangerous intervals. Okay, and now I don't have a sparse sequence of dangerous things that I want to remove. I do not have T1 and T2. I only have this big T, and I can create layers in this Cantor-like set. So I remove for big T equals 0, big T equals 1, big T equals 2. But the problem is that for each fixed big T, I have big T things that I want to remove. And this big T has to fight with this proportion here, okay? This is why I cannot allow myself to go smaller than this volume. So I have to have precisely this proportion of things that get removed. Okay, maybe this was slightly confusing, but essentially this is the idea. And to achieve this sharp non-escape of mass, this is not something better than what Kleinbach and Margulis proved. It's just essentially based on the removing procedure that you set up. So it's based on the inductive hypothesis. So it's not true everywhere. It's true in the sets that you're left with. Once you start removing in the sets that you're left with, you're good enough to achieve something stronger that the non-escape of mass that you would be able to prove in general. Okay. Okay. So this was just an idea. Hopefully, I haven't confused you too much. But okay, this is the picture that you should have in mind. Okay. So I think I'm done.
More questions?
Yes?
Can you extend your result by multiplying also by the p-adic absolute value of Q?
By what, sorry?
The p-adic absolute value of Q.
So you mean a p-adic version of this? Probably yes, but okay. In theory, it should be easier. So take this with a grain of salt. It should be easier because BADZIAHIN's result came after the p-adic version, and the methods used in the p-adic versions were essentially a simplified version of what he used in the global version. So one could predict that probably the same is true here, but I don't know. I don't know, because it's after all, dynamics here plays just a role, but only to a certain extent. So dynamics is essentially in this case is a cute way of ordering the sets that you want to remove. But at the end of the day, what you actually use is some kind of geometry of numbers to remove to prove this thing here. Okay, so probably the same geometry of numbers argument works in the p-adic setting, but I haven't checked it. I don't know.
Do you have some intuition about the log-log factor? Why is it necessary?
Yes, so I thought about it quite a while, and okay, it's complicated. It's not easy to explain. I'll try to do my best. So let's see. So the point is that, okay, so you want to prove something like this. Okay, so fix your time t. Okay, and you want that for some interval I prime fixed. Okay, the bad part occupies a certain proportion of that interval. Okay, so of course this cannot be true for any interval, right? Because if your interval is too small, it could be entirely contained in this dt, right? It could be entirely contained in the bad part, right? So if you zoom in too much, you can never achieve the right proportion. So you have to be well away from the single components of this set dt to see the right proportion, right? And this is where the log-log factor comes in. So essentially getting rid of this log-log factor would mean being able to zoom in, so to make this interval I prime essentially of the same size of the intervals that make up this set dt. Okay, so if you would want to remove this log-log, but it's really too much. So I think there is still some. So this is not possible. You cannot zoom in too much and see the right proportion, right? But the thing is, I believe there is some kind of overcounting. There is some kind of intersection between these sets dt that we're not still able to see that much. And especially in this, where did I write it? Yeah, so in this case here, right? So by zooming in, I mean changing this parameter big T, okay? But for a fixed parameter dt, you have many t1, t2 that you consider. And here you can be essentially losing a lot because these dt1, dt2 that you consider essentially as completely separate might intersect. So probably if one wants to do something to get rid of that factor, it should be here, but not by zooming in too much. So I'm not sure. Maybe I was a bit. I'm not sure if I gave a clear idea, but.
If there are no more questions, let's thank Reynold again.